Okay, so discussing chapter 8, our second chapter investigating the solar system and turning our attention from the solar system as a whole, which we did in chapter 7, to the planet Earth. The cover image here shows CO2 levels fluctuating over time, over thousands of years, in fact, hundreds of thousands of years, going back 800,000 years. And this is based off of the CO2 that gets embedded in either sedimentary levels or ice. And so this is how scientists are able to go back so far and find measurements, from those atmospheric depositions. And then we can look at the current change, a change that hasn't shown up in the last 800,000 years. Uh, there, I mean, the planet has gone through some more dramatic changes, of course, in on the time scale of millions or hundreds of millions of years, where the atmosphere was significantly different. Of course, there was a point where the atmosphere had no oxygen in it at all, for example. But this is on this time scale of 800,000. We certainly don't see anything like it. All right. So we will talk more about atmospheres, but first we're going to look at some other key characteristics of Earth. And let's see. Yeah. So there's not a summary for the different sections. So what to expect as we go through the slides is going to be a bit about the interior composition of the planet, the core, how we know about the different layers of the planet, and then the Earth's magnetic field, which is created within the planet, but of course extends outside because the effects of magnetism can be experienced on the surface. That's how you can use a compass, for example. And then how the magnetic field extends out into space, how that has a significant impact and an importance. And then we'll then continue to kind of talk about the surface of the planet in terms of tectonics, some of the importance of those resurfacing features of that are fairly unique to our planet within the solar system, and then kind of finishing up with the atmosphere and questions such as the one that are that would have answers related to the cover image here. So what does that tell us in general? Well, we're going to be working our way from the inside out. We're going to start on the inside of the planet and kind of work outwards. So the planet has a size of 1 and a radius of 1. But of course, those are not in metric based units, right? This is more of comparative units as we talk about the solar system. Because when we're going to talk about other planets, we're going to want to compare them to Earth. It's a natural reference. And so it's very common, just as we have the astronomical unit, which is an Earth based unit because it's how far Earth orbits the sun. Well, same thing here. We're going to talk about planet size in terms of Earth radii and planet masses in terms of Earth mass. The actual values um, for these units in base units, you can look them up in a table in the book, and sometimes they would come up in a calculation. But for comparative purposes, we'll stick with these. The density, well, we all just call it a density of 1. In fact, if if there is such a reference density, it's going to be water. We talked about that last time in chapter 7. When we have a comparative density, we compare it to water. We say that the planet is 3 times denser than water, for example. And so this value right here would be 5.51 times denser than water because 1 gram per cubic centimeter is the density of water. All right. So that's basically where the gram was defined was from that concept of that's how much mass water had. So there's more modern ways of defining it, but approximately that, for pure water, density is 1 gram per cubic centimeter. So in other words, Earth is 5.5 approximately times denser than water. That does mean that Earth is the densest planet in the solar system. It's slightly denser than Mercury, which is surprising and probably just has to do with particularly heavy planetismals that were involved in the formation of Earth, or is extra evidence supporting the most popular theory of the moon's creation, our moon's creation, which was that a large impact later in the formation of the solar system sheared away a lot of the upper surface of Earth, which then coalesced to form the moon, which started off much closer to Earth than it is today and has been drifting away ever since, or rather losing energy due to tidal friction and then becoming repositioned in further and further orbits, which is a measurable ongoing process. And so that means that that lighter material that would have already risen to the surface in in a process that we know the term of, but I won't say the name because we're going to see it in just a second. Well, that lighter material near the surface of the cooling or already cooled early planet Earth would have then been what the moon ended up being made out of. And the moon itself is in fact particularly low density, lower than we would expect it was made independent of Earth or side by side. Well, that means that we were left with all the denser material. So that gives us a denser overall, or just value, really. What in the what other way I could say that is that it gives us a overall greater amount of mass per volume. Okay, so enough about that. Orbital period, we know 365.2 days. That is the full time it takes the planet to orbit around the sun. And of course, that 0.2 days shows up sometimes when we're doing calculations. Often you'll see it as 0.25. Here it's approximated as zero point 0.2. The semi-major axis, again, in units that are specific to Earth, 1 astronomical unit. You can convert this to kilometers or meters if necessary, but comparing between planets, it makes sense to stick in AU. The rotation period is 1 day. I suppose you could also convert this to seconds, right? Which would be the base unit. That would be simply multiplying by 24 and then by 60 and by 60. But this is the considered the rotation period again, so we can compare our rotation period to that of the terrestrial planets or the Jovian planets. And as you know, we have an orbital tilt, pretty significant one at 23.5 degrees. All right, so remember that word that I was hinting at just a moment ago? It's differentiation. This is why the lighter material would have been, or the less dense material would have been near the surface when the moon was formed, when some of that material was ejected into space. So, planet formation. Okay, these are the ideas we touched on briefly in chapter 7 and the slides related to that chapter. So Earth formed out of planetismals. Remember, those are all these smaller, sort of dwarf planet-sized, early building blocks of the solar system that would smash or shear into each other and then would create molten planets. So the early terrestrial planets, and really actually the early Jovian planets, would have been entirely molten. They would have been composed of rock that was heated to the point that it was liquefied. So it would be almost like the entire planet was lava, or that the magma that we know is underneath the ground would be all the way up to the surface. There would not have been a cooled surface. Just like if you see lava flowing in an active volcano, like on the island Hawaii, there's little sections that have cooled down and have like a temporary crust. Certainly that would have been the case, but there would have been no large, stable, cooled surface, sections of the surface. As cooling occurred, as the planet was able to cool enough for the surface to become completely, rigid and solid, there was a sinking of the denser material and a rising of the less dense material, and that is what we call differentiation. So it's a separation, but the term is differentiation, and that causes layers in its interior. When we look at any planet, so any celestial body, any solar system body that is big enough and therefore round and therefore classified as a planet, we see differentiation because the idea, the physical concept of becoming a round or spherical object goes hand in hand with being differentiated. You can't get one without the other, at least not to a good like kind of approximation. So that's the idea because you have to be completely molten to you have to be big enough to be completely molten, and that means you're big enough for gravity to get that spherical shape, cause or create the spherical shape. To understand the layers that exist today and to explore them, scientists can't just drill a hole into the planet and go down to these different layers because the distances are too great, the engineering is unfeasible, and even if we could say drill through the entire crust of the planet, we couldn't really go any deeper because it would just be too hot and too unstable to actually support any sort of even narrow column if just like almost like a pipe that we were trying to put down into the planet. There have been actually continued attempts to drill through the entire crust with the Russians and Russian scientists and kind of like Russian-backed operations making the greatest progress and really sticking with trying to drill all the way through the crust. But it's never really gotten beyond 30, 60 kilometers, and the crust is close to 100 or 150 kilometers in thickness. So if we can't just directly explore, even by, just sending a small wire down there, then how do we know what the interior of the planet looks like? We have to instead send vibrations through the Earth and see how those vibrations travel. And the way in which different types of waves travel through the interior of the planet actually gives us a really detailed picture. And sometimes those waves are created on purpose due to a basically an explosion for the purpose of investigating the waves that are created from them. But more often, they happen naturally because of earthquakes and a whole network or really grid of observing stations take all that data that's coming from earthquakes and use it to calculate the thicknesses of the different layers of the planet. And obviously the resolution today of that data is incredible and just continuing to get better. Much of the planet at this point is covered in almost like a kilometer, or maybe 10 kilometer by 10 kilometer grid of stations that can read seismic waves. But on a just fundamental level, and what's been happening over the last century is just confirmation that the layers even exist in the first place, and some good approximations of how thick they are. So the reason this really works, the reason we can investigate the interior from earthquake waves is because earthquake waves have two types. In other words, whenever you create a wave in a solid like rock, the wave that's created, the vibration, the mechanical wave is it naturally taking two forms. One form is called an S wave, which is an up and down wave. Like just like here in the picture with a slinky, which obviously isn't like rock, but will serve as a good stand-in in this case. The up and down motion is shown as, well, just that, right? So we have what's called the amplitude, which is the displacement from where the slinky would be if it hadn't been vibrated or shook up and down. And that amplitude is relative to this horizontal line, and it's perpendicular to the direction of motion of the wave, which is shown by the green arrows, and the letter V representing velocity. So the S wave is also known as a transverse wave. And it's one of the two types of waves that are created in any solid due to, an earthquake in this case, but just any, output of energy in general. They do tend to travel slowly, and most importantly, for our discussion, they are blocked by liquid. They cannot travel through liquid because they have to have some sort of restoring force to bring the wave back down. So liquid doesn't have a elasticity. It just flows by definition. And the same would apply to a gas. A gas also does not have an elasticity. Whereas, of course, this slinky does, right? A slinky can act like a spring. It has a natural kind of spring back force, which we call a restoring force. So does rock, so does any solid. Okay, so S waves, in other words, transverse waves, cannot travel through the body of a liquid. If you're wondering, well, what the heck are ocean waves in that case? Because after all, the ocean is a liquid, right? It's water. And doesn't this look a lot like a wave that you see, in the ocean? Well, that's because that's a surface wave. And on the surface of a liquid, you can have a transverse wave, the equivalent of an S wave, but not underneath the water. Okay, you can't send an S wave through the deep water or just anywhere beneath the surface. So, well, there you go. All the liquid we're going to be talking about is going to be liquid that's underground. We'd have to be sending the wave through that body of liquid. It can't be done if it's an S wave. The terminology S wave is specific earthquake jargon. It's actually not used outside of the study of earthquakes. In physics or any physical science or engineering, we call this a transverse wave. Okay, so that whole S wave is really, really specific. Okay, and then likewise, terminology for earthquakes, P waves are the other type of mechanical wave that can exist. And the term for them that's used in every discipline other than seismology or the study of earthquakes is longitudinal. So, in other words, P waves are longitudinal waves. And these two types of waves, and the reason we care about them, are shown right here that P waves can travel through a liquid. Okay. S waves can't, but P waves can. They also travel more quickly. Okay. An example is a sound wave, and sound waves travel just fine through liquids or gases. The way that they travel is by having displacements that take the form of either condensing. So here we can see the springs or rings of the slinky getting more condensed, or stretching. So they travels through stretch or condense. And the reason that this doesn't require an elastic property, unlike transverse waves, is because in the case of liquids and gases, this is just going to be a rarefication, so less molecules in a particular volume, and in the other case, just a increase in density. So we have basically a condensation and a rarefication. And those processes absolutely can, create a force and a chain reaction that continues to transmit the wave. So longitudinal waves travel just fine through bodies of water, bodies of liquids. And again, for earthquakes, we call them P waves. So these two types of waves can be used to map the interior of the planet. And that's what this figure is showing us. Imagine that this is the source of an earthquake on the surface of the planet, or at least near the surface, because that's where actually most earthquakes are going to occur, even when they have a deep epicenter, which you might have heard an earthquake described that way. It's still only going to be tens of kilometers underneath the surface, which is tiny compared to the overall radius of the Earth being, over 6,000 kilometers. So it's really safe to say that all earthquakes occur very near the surface and certainly all in the crust. So there we go. We got our earthquake. It's going to create waves. The waves are powerful enough to travel all the way through the Earth. Yes, they decrease in intensity with distance, and certainly you would not notice it in your everyday life if you were on the other side of the planet. But with a sensitive device, it's no problem at all to measure an earthquake on the completely other side of the planet, even a rather small earthquake. There's always a certain amount of background noise, right? What if a truck drives by? That could literally create, a vibration, a train or something, even someone walking near the device. But accounting for all of that and usually like filtering out certain types of vibrations and just placing detection devices in isolated areas, so like the middle of fields where there's not nearby roads or people, is and obviously having replication, so lots of different detection devices. It really is becomes a complete doable task. Lots of earthquakes are measured on the other side of the planet. Okay, but not all the waves make it to the other side of the planet. And that is how we can map the interior. Notice the P waves that travel, right, radiating outwards. And when they encounter a interface between the mantle and the outer core, there is a refraction at the boundary. Well, a refraction at the boundary implies a change in the composition. Now, it could just be a change in the density and not a change in the state. In other words, not a change from solid to liquid or vice versa. Okay, but it does imply some change. And so that's, I'm referring to this right here, this bending. A refraction is the same idea as when light passes from air into water and it bends, which is the effect that causes, say, a straw in a glass of water to look like it's discontinuous and enlarged inside the water versus the part that's sticking up into the air. So that same idea is called refraction. So we have refraction of the wave, part of the story, but then notice that's all the P wave. The S wave, that wave that's called a transverse wave, doesn't travel through the outer core at all. So here we can see that it just skirts along the surface and is not refracted. There is no refracted S wave, only a refracted P wave. Furthermore, for the wave that hits the interface between mantle and outer core directly, and therefore would not have refraction, because the one case where refraction doesn't occur is for a direct hit, in other words, perpendicular wave direction relative to surface. Well, notice what happens to the S wave. It just disappears. The energy would actually get reflected backwards. And that's because the outer core must be a liquid. An S wave can't travel through it. It's got to be a liquid. All right. And only the P wave can. That means that on the far side of the planet, P waves are experienced, all right, because they can make it all the way through, but there are no S waves to detect because none of them would have made it to the outer core. And because of the refraction angle, and then a shadow zone can show up and will show up, which is where very weak P waves are detected, much fewer of them. And this can then lead to a calculation of the actual density of the outer core. All right. So I already told you the answer, that because the S waves cannot travel through liquid, the outer core is a liquid. Okay. Because there's no S waves. So sorry, so we know they can't travel through liquid. We don't see them traveling through the outer core. Therefore, the outer core is a liquid. That's the chain of logic there. So that's the idea. The outer core is a liquid. Is the mantle? Well, no, clearly not, because the mantle does have S waves traveling through it. Because we can feel them, right? We can see them show up at other locations. It allows for the transmission of S waves. The mantle does, kind of have some variety and start becoming more like a liquid, but it's only once you get to the proper outer core that the interior of the planet is fully liquid. The inner core is not. The inner core is a solid. And that's because despite the high temperature that caused the melting and therefore the liquid nature of the outer core, the high pressure ends up dominating at the depths of the inner core, causing the liquid to turn back into a solid. So it wants to be a liquid because of the high temperature, but the incredibly high pressure due to all the mass pushing down on it from above means that the inner core is in fact just a superheated solid. All right. So moving right along to the changing crust. So, like I said, we're moving outwards. although we'll jump back a little bit inwards when we talk about the magnetic field. So, are there craters on the surface of the Earth? Well, uh, do you know of any craters on the surface of the Earth? And you might not. There are, okay, but not many. So Earth formed out of planetesimals, as we know, right? Creating a hot ball of molten rock. It cooled, differentiated, caused layers in its interior. However, unlike the moon, craters aren't visible on the surface because the crust is young. The planet's old, but the crust, the surface, is young. Whereas with the moon, the surface is old. With a few exceptions, the Maria, the mares we talked about, the lunar mares, where there has been some lava flow to cover up the old crust and therefore obscure it from view. Well, that's, the exception to the rule on the moon. But on Earth, almost everything is getting covered up on a regular basis. So we simply don't have craters that last very long. But why is that? Why is the Earth's crust kept young? Well, I won't ask for an answer because you'd have to give me lots of different numbers based off the options. It's both one, two, three, and four. Okay. Plate tectonics, which is the moving of the plates, thing, as you likely know, leads to earthquakes. A kind of actual subcategory of plate tectonics, which are rift and subduction zones. So rifts are where the plates are spreading apart and new plates are being created. There's a number of locations on Earth where this is occurring. And subduction zones are where the higher density plates are sinking underneath or sliding underneath the lower density plates, usually oceanic plates sliding underneath continental plates, and therefore getting melted only to be recycled and become new plates again in a rift zone. Fault zones, which is part of plate tectonics, usually where they rub together in particular, like a slip strike fault, and volcanoes, which are often a byproduct of plate tectonics because of the release in energy due to melting subducting plates. Here we have a map of the tectonic plates throughout the Earth. So the crust is separated into individual plates, and this map shows some of the major ones, like the North American plate and its boundary with the Pacific plate. And some faults like the San Andreas fault running between that plate boundary. There are lots of smaller plates. For example, you can see that there's a line up here that says Gorda plate and doesn't point to anything that's bounded by thick red lines. Because if you were to look at a more detailed map of the plates of the Earth, you'd see that there are cases where there's little fragments and much smaller ones. But this map does show the largest, most major of the tectonic plates. These are essentially just like big pieces of broken crust, or at least movable crust, that are always sliding relative to each other, always getting pushed away from those rift zones where new plate matter is getting created, and also sliding underneath each other. And as far as the driving force of all that sliding, crushing, and crunching, well, it's because primarily of those rift zones. So if we look at the Mid-Atlantic Ridge, which is a rift zone, and the Mid-Pacific Ridge right here, or this region called the Pacific Antarctic Rise, and then kind of cut off, we can end up with the Mid Pacific Ridge. We can see it gets split by the map largely, and then also some rift zones right here that run right up to or through the Indian Ocean. So the Southeast Indian Rise, and what lets us know that all these lines that I've mentioned just now are these rift zones. Well, it's the direction of the arrows. Notice the arrows point away from the red line. That's because these are plates that are pulling apart, but they're not pulling apart for no reason. Rather, they're getting pushed apart by a upswell of newly created plate matter. In other words, all of these ridge lines, all of these rift zones involve long lines of small volcanoes, essentially just a wall of volcanoes where magma is rising to the surface, erupting out almost always under the ocean and can, solidifying into new rock. And then as that process just continues, that new rock pushes away the rock that solidified previously, and it's just ongoing sliding away from that rift. And that means that there's just this gradual creation of new ocean bed, and then those new plates have to go somewhere, and then they push into the other plates, causing the continued motion, right? Because then that plate gets pushed out of the way. Like I said, might slide somewhere else or slide under another plate. And so it's just this ongoing process. Also, of course, driving the eruption of volcanoes. If you think about the so-called ring of fire, well, that's because of all of the interaction between plates that are being pushed by a rift zone interacting with other plates, and all that melting and release of energy leading to long lines of volcanoes. So this whole process does require water, because notice that all the rift zones happen underneath oceans. And well, it's always kind of been a interesting idea. Well, is that necessary? And a lot of modern study of earthquakes and geology and earth science has shown that it's not just a coincidence, that really the idea of having the water pushing on particular plates, and those plates being the oceanic plates, that's why they kind of take that role of being the higher density ones that are continually being created. And so in other words, having oceans seems like a necessary ingredient to having plate tectonics, which is quite interesting. Right? Yet you can't have one without the other. There's a recent paper from 2017 talking about the kind of, which you can see in the abstract here. All right, so now I'm just going to run through some of the terminology that I've mentioned, but I just want to put it out more formally. Okay, so tectonic plates, subduction. Okay, so subduction is when you have a plate sliding underneath another plate. So this statement here is just general. The plates move, collide, push underneath each other. Okay, which is the subduction, but push up mountains, grind together, open holes for lava. So this is just all the things they can do, with the underlined part being, the part of that sentence that refers to subduction. All right, an example is the Pacific plate, right? So an oceanic plate. That's what's shown here. This would be the Pacific Ocean, we can see above. And that Pacific plate is sliding underneath the continental plate, the North American continental plate. And then that oceanic plate is being melted. Okay. And so that's where the new material can come from to create new oceanic plates of those rift zones. But not all that new material is just going to make its way thousands of miles to the other part of the mantle to be recreated into new crust. Although eventually a lot of it will, and it does that through these big kind of currents, so to speak. These big, what are actually called big convection cells, because there's big kind of rising and swelling of the magma going on. Well, to some other amounts of that recently melted oceanic plate are going to find paths due to, kind of imperfections, flaws in the continental plate. And those paths then become these magma chambers, and then the magma chamber can crack and create another one and eventually rise up to the surface and form a volcano, usually just a little bit kind of inland from the boundary of the continental plate and the oceanic plate. And that's, in this case, the Cascade volcanoes, right? So a line of volcanoes created as a direct consequence of subduction of plates. All right, and specifically the subduction of an oceanic plate under a continental plate. Just to repeat, oceanic plates are denser, continental plates are less dense. So when they interact, The oceanic one always slides underneath. But not all plates are just sliding underneath one another. Sometimes they're rubbing against them, against each other. And that's where you have the strike slip faults. So that's that lateral motion shown here, right? One plate kind of sliding to the side, the other in the opposite direction. The San Andreas fault is an example of this type of plate interaction. So it's an interaction at the plate boundary, but a grinding together instead of a pushing under, right? Can also create mountains, certainly, all right, but not as readily, and is not going to lead to volcanoes because there's no big correlation with melting, right? No plate is getting pushed down and getting melted. Another case of fault, or rather plate interaction, is going to be continental subduction. So continental subduction is where a continental plate is kind of pushed directly into another continental plate, and even though they're both, comparable density, and there's not a natural case of one being able to slide underneath each other, one, it's not an easy thing of one sliding under the other because it's much denser. Instead, they kind of crash into each other. Eventually, one will slide underneath the other. But because of their very similar densities, there's much more mountain creation, much more uprising, and a more kind of dramatic interaction. So this is, really where you have, because it kind of makes sense for more continental plates to do that strike slip, really kind of just like rub against each other as they maybe get twisted and rearranged. But every so often, when the collision is at just the right angle, one of the continental plates is actually forced downwards. This leads to some of the biggest mountain ranges that get created throughout Earth's history. Case in point, like Rocky Mountains, but also the Himalayas. The Himalayas are a great example of a continental subduction with the Indian plate sliding underneath the Asian plate. All right, so that's all the stuff that's resurfacing the planet. Well, that's happening continually. So if a crater is located somewhere, it can get erased by a volcano. It can get erased by, just the fact that that whole section of land doesn't exist anymore because it got pushed down into the mantle. Any number of dramatic events over millions of years can completely erase a crater, right? But even more, we've got weather, right? So erosion, from just from rain, from wind, from ice, such as glaciation, is going to sculpt rock, right? And that's able to cause mountain ranges to disappear over, long periods of geological time, hundreds of thousands or millions of years. Well, if whole mountain ranges can disappear because of erosion, certainly a crater can as well. All right. So erosion, right, caused by all aspects of weather, the motion of tectonic plates, lava flow from like volcanic eruptions, all of these erase signs of craters from Earth's surface. So craters just really don't stand a chance of lasting that long. But they do last a while, so how long, right? Well, you can definitely find lots of young craters, right? So, for example, a famous crater here in North America, in the continental United States, called Meteor Crater, not the most creative name, right? But located in Arizona, quite noticeably a crater, the kind of thing that you would expect to see on the surface of Mars, right? Especially with kind of the reddish color. It's 160 feet wide, right? And it was, or rather, it was created by a 160-foot wide meteor. The actual diameter is a mile, and that's kind of the typical ratio here. Is that the the crater is much wider than the asteroid that created it. The rock that created it. It's interesting that the slides refer, and they do this more than once, refer to the the object that created the crater as a meteor. Um, this term really usually gets used just for the visible event in the sky. So if you see a meteor shower, well, the meteors are the streaks in the sky. They're not the object itself, which is was an asteroid when it was in space. If some of it survives to the ground and isn't vaporized on impact or just burns up in the atmosphere, then what's left over, whatever pieces are left over, are called meteorites. Well, I think the idea here, calling it a meteor, is saying, okay, well, this size is kind of like how big it would be when it was airborne. And so since it's referring to when it was that streak in the sky, kind of giving it that size while it was burning up in the atmosphere, or rather, which part of it actually made it down. Um, is not the way it's typically used, but I think is not entirely wrong either. There are because there ends up being actually a few different terms, even these things called bolides. So there's quite a bit of terminology for meteors and impacts. So I think we can let it go, but I think it would have been fine just to call it a 160-foot wide asteroid as well, and just give it its size when it was still in space, and then there'd be no argument to be made. But anyway, only 50,000 years old because that's kind of the age where we're going to really see a pristine crater like this, right? There's some erosion around the lip, but we can clearly see that shape, right? Where the crater kind of, looks like this blister because the edges get pushed up as all the energy is released. All right. There's not, too much evidence of kind of like the spew that comes out. And that's because that would have been much easily blown away by wind and washed away by rain. Whereas if you look on the moon, for example, where there's no atmosphere, so no wind, then you actually see like this the spew of rocks and dust that come out from the explosion as things resettle from due to the influence of gravity. So that ends up getting probably lost within decades or hundreds of years, but overall, we still have a nice looking crater. There are craters that go into the tens of millions of year range, but they become it harder to discern. Sometimes they look like a different feature. So there's like craters up in the far north. There's one known in like Siberia, but it kind of just looks like this long sort of ring lake. But there's actually a 200 million year old crater. And then even more famous, we have here a 65 million year old crater, the one that's associated with the extinction of the dinosaurs. So there's kind of lots of supporting evidence that it was a impact that wiped out the dinosaurs. And then this is the crater that further supports that theory of dinosaur extinction because it's the right age and would have been a dramatic enough event to cause the climate change that would have led to the extinction. And the crater, however, is not easily seen. You're not going to notice it on a kind of a ground-based survey or anything. Instead, you're going to see it like with satellite imagery and radar, because a lot of it is under the water. And so we're really just looking at, kind of this sort of subtle signal with half of it, above land on the coast of the Yucatan, and the other half underneath the sea in, the Gulf of Mexico. All right. But it's about a 5 mile wide meteor that caused the crater, and the crater is 93 miles wide. And so this is one of those extremely rare events that is, as far as we know, only happen a few, or only have happened a few times throughout Earth's history. The fact that this one was 65 million years ago is more of a kind of, just the randomness of the events rather than saying a impact this large happens every 65 million years. Instead, an impact this large really, as far as we can tell, would happen on an average of every 500 million years. Right. So only about, maybe 5, 6 of these impacts since, the Earth was fully formed. And then we have the crater lake, which actually isn't a crater at all, right? It's from the collapsed caldera of a volcano. And so the fact that we call it Crater Lake is really a misnomer. It's not well named, right? I might complain about the crater in Arizona lacking creativity in its naming, but this one lacks accuracy. So we should really call it Volcano Lake, right? Because it really has nothing to do with craters. It's got that circular shape, right, and a ridge, but was not created by an impact. Rather, as it says, it is a collapsed volcano. Okay, so We're going to go ahead and pause. I wanted to get to a good stopping point. I hadn't forgotten about break. And we'll take a 6-minute break, take us up to 9:20. At that point, we will resume with the slides. All right, so continuing with our lecture on Earth, we're moving on to Earth's magnetosphere. So what is that? Well, the name kind of says it. It has to do with magnetism. So it's the magnetic sphere, right? And the term here is, referring to sort of the influence of our magnetic field. So I'll say magnetic field a lot, and then sort of the whole region of space around Earth that's affected by that field is called the magnetosphere. And interestingly, the edge is called the magnetopause. It's kind of a strange name, but you'll see it in a figure in a couple slides. So first, to talk about Earth's magnetic field, we need to talk about magnetism briefly. Kind of like we had to talk about the basics of waves and the two types of them in order to discuss earthquakes. We have to sort of get back to the basics here. So when you have a magnet like this bar magnet shown here, there are two poles, a north and south pole. So every magnet has two poles. Fridge magnets do as well, but all of their poles are lined up like sheets. So it's like a bunch of north and south, so that you can stick it to the side of something. Bar magnets, of course, have just one big north and one big south. When you have a bar magnet, which is a great demonstrator of this concept, you have something called field lines, and specifically magnetic field lines. These represent the magnetic field in sort of an abstract way. So they tell us where the field is pointing and how strong it is. So when field lines are more closely packed together, that means stronger field, stronger magnetic field. And when field lines are further apart, it means weaker. And then the direction of the field line tells us the direction of the force that magnetic field would exert on another magnet or on a charge or current. Because that's a big idea, is that magnetic fields can exert forces on charges. Okay, like an electron, for example. And by definition, magnetic field lines connect the North Pole to the South Pole. There's a really similar concept with electric field lines, and in that case, they point from positive charge to negative charge. So you can think of that as a parallel, but we'll stick to magnetic field lines here. So we'd have a magnetic field line that comes and then goes along these iron filings, kind of tracing them out, and then comes back down to the other pole. And then the direction, like I said, would be from north and then go to south. So this would be the magnetic field line. But how was I kind of able to estimate that path, right? Why did I know to draw it with this shape? Because I just followed the iron filings and the way that they make these lines. Because it turns out that if you have a bunch of loose pieces of iron, which is a metal that can be easily magnetized, and then you kind of shake it around so it's distributed on a flat surface, and you lay a magnet on top, well, because of that property of iron, it'll end up being easily affected by the field, and therefore line itself up because each little dust piece can move independent of the others, and so every little bit will line up with the fields. And so, they will end up with gaps where there's no field lines or weaker field lines, and then thicker bands of the iron filings where the field lines exist. So it's a way of kind of really visualizing is otherwise an abstract idea, the magnetic field lines. All right, so here you can see, right? They've removed the iron from the picture and just drawn in the field lines like I did. So you can see all these different field lines connecting the North Pole to the South Pole. And again, where the field lines are more closely packed together, that's stronger field, and where they're more, widely distributed would be weaker. So I just circled a region of strong and a region of weak field. Okay, so now imagine that you took a compass. Now, a compass has a needle that points north. And the way most compasses are made is they have the north end of colored red and the south pointing direction colored white. So here we see a, a compass put down right on top of the field line. And just like the iron filings, the compass would be a way to see the field. Because what is every compass? Well, it turns out that every single compass is just a bar magnet floating in liquid. It's floating in liquid so it can easily spin and align itself with whatever field is nearby, usually with the Earth's magnetic field. But you could also have a compass line up with a stronger magnet. If you bring a big magnet near a compass, it'll get pulled in the direction of the magnetic field created by that magnet, because that local magnet would overpower Earth's magnetic field. So we see that compass with its needle pointing right in the direction of the field line, right? So then what does that mean about Earth's magnetic field? Because if we look at the compass, right, what is the compass? I said it's just a floating bar magnet. That means that every end of the compass is a north and south. So every compass, if it's just a floating bar magnet, has a north end colored red, just like the original bar magnet, and a south end colored white. All right. Well, if this is how the compass looks when you place it above the north pole of the bar magnet, and then if you take another compass and you place it down here, kind of below and off to the side of the south pole of the bar magnet, and then you put yet a third compass over here to the right side of the bar magnet, they'll all align themselves as shown, right? And why do they do that? Well, because of a principle with magnetic poles, which is the same exact principle for charges, which is that opposite charges experience an attractive force, but like charges or like poles experience a repulsive force. So again, for magnets, if you have two north poles, they will push against each other. So that's a repulsive force. If you have two south poles, they'll push against each other, also a repulsive force. But if you combine a north pole with a south pole of a magnet, they will pull towards each other as an attractive force. Okay, so opposites attract, likes repel. So what we're seeing is exactly that, because the compass is just a magnet. That's all they are. And so because of that principle of, opposites attracting, the south pole of the magnet is attracted to the north pole of the larger bar magnet, the thing that's creating the magnetic field. Okay, well then if you look, below the south pole of the bar magnet, now the north pole of the compass is attracted towards the south pole of the bar magnet. Okay, so with that idea, I do want you to answer this question. Under the north geographic pole, so far we've drawn this picture of the Earth, and I'm saying that Earth acts like a bar magnet. I'll elaborate on that idea in just a second. But for now, just imagine there's a giant bar magnet inside of Earth, because effectively there is. Okay. So up where Santa lives, North Pole, okay, is there a north or south magnetic pole? Which is it? Okay, so Kylie says north magnetic pole under north geographic pole. Okay.
But I feel like it could also be south no though now that I think about it because I'm thinking like if it's a magnet, opposites attract. So like positive magnet, negative magnet, or like positive charge, negative charge. So like I don't know, maybe I'm just kind of
No, that's good. I'm so glad that you revisited it in your mind because you're right, at least on second thought. And it's really interesting because this is one of those ideas where I literally just talked about it, right? I just said and that there's this whole idea and I described all the field lines. But when I ask the question, almost everyone will give the answer that it's got to be a north magnetic pole under the north geographic pole. Again, even though I just explained why it couldn't be, and it's just because it's such a counterintuitive idea. But you get used to it. I can say with practice over the years, I've come to accept it, and it's not just like some weird decision that scientists came up with where they said, "Oh, wouldn't it be funny to make the North Pole a South Pole?" It's because there's not really a good option. If we called the North the, okay, let's think about it this way, right? So because I have a magnet and the magnet's got a North Pole and a South Pole, right? So if I wanted to call the geographic South Pole, which is actually, as we can see, a magnetic North Pole. So if I wanted to call that north, right? And that, if I said, okay, well that's got to be the north direction. Well, then I'd take my magnet and I would then say, okay, well now, my magnet has the south pole of the magnet pointing towards the North Pole. So it'd be like, okay, well then it's still going to have that disconnect where the magnet will always point the opposite direction. So I think that when these definitions were made, they made, scientists and decision makers made the reasonable came to the reasonable conclusion that we'll just base the geographic names off of the direction of the magnet rather than the direction of the field that the magnet is being pulled by. So we've got, when you hold the compass, you take your compass, the north end of the magnet points north. Yeah, okay. But it's pointing towards a south pole because it has to be. Okay. So it's the it's always going to be reversed
I thought of this
because
as a
yeah.
trick. I thought of this as a trick question as
Oh,
well,
okay.
to be honest,
So
because
like a trick on the so I was just
yes,
explaining all this stuff and then I was okay,
yes,
that's fair.
because
That's
when
fair.
Kylie made her point, I was like, oh, she's totally right. But so then it's an automatic thing that it's going to be opposite. I mean, are
Yeah.
we automatically saying that they're attracting? So we know
It
they're
has
always attracting,
yep. So it
right?
has to be opposite. Exactly.
Okay,
So
because
yeah.
they're
It,
always attracting, so it's never repelling. It's always going to be an attraction on that.
well the opposite poles will always attract.
Right. But I mean, like
Yeah.
when you say like the question under the North Geographic, there's always going to be um
The opposite the
the
opposite
opposite,
pole.
right?
Yeah.
So
Yeah.
okay, okay. So that's fair.
And
Okay. Always.
yeah, and okay, you know what? I have a cool idea too that will directly relates to that. So so just to jump ahead, there's this, and there's no reason not to, because this kind of talks a little bit about how the field is created. We can get back to that. So an interesting thing happens every like it's about every God, what's the time frame? I think it's 50,000. But yeah, so about every 50,000 years, which is, quite frequent. There's all these different, time scales. But anyway, so every 50,000 years, there is a flip in the magnetic field. And it's really clearly basically indicated by the mag or the lava that cools on the ocean floor at those mid oceanic ridges, right? And where the plates are spreading apart, because if you look at it as the rock cools, it actually saves the magnetic field because the crystals will line up. So if you know what to look for, you can easily see which way Earth's magnetic field was pointing when that rock solidified, when the lava dried into solid, cooled and dried into solid rock. So what scientists are really easily able to see is this changing polarity. So they see that at some point in the past, the magnetic field pointed one way, and that would be this band that's furthest from the current rift, right, where the new rock is being made. And so then we look at it, we say, okay, well then the magnetic field pointed, one direction, it flipped, and the region of reversing polarity is showing, or actually the white is where it was flipped, and then it went back the original way and then flipped again. So in other words, each of the sort of oranges or peach colored ones, and then the red one, all of these are kind of the current direction. So this furthest one, peach, would be the normal magnetic polarity. So would the orange, and so would the red. So in all those cases, the geographic North Pole it would be a magnetic South Pole. All right. But then every other 50,000 year period, you have the poles completely flipped, where now what's currently a magnetic South Pole up north, right, would then instead be in Antarctica, right, down beneath South America and Australia and South Africa. So okay, well, what does that mean, right? Well, if that happened tomorrow, right, if the field just flipped, and now all of a sudden the south geographic pole is now a south magnetic pole. Well, wouldn't that just resolve the issue? Wouldn't that just make it so that now we don't have this weird disconnect? Well, no, because now all of our compasses would tell us that north is towards the south. Every single compass would have that north end of the magnet, of that little floating bar magnet, pointing south. So then what, right? We just we have to say that all compasses, point the wrong way, I guess. So you
Oh
see how
man.
yeah, so there's always, but there would always be that disconnect. You either have to have all compasses point the wrong way, or you have to have your pole names not match. There's you know there's no way in between, because we could just rename the poles and say that every bar magnet, its North Pole is now its South Pole, and maybe that's what we do. But that you always, yeah. Yeah, they are, because opposites attract and the like ones repel. Yep. And it could happen that the poles absolutely could flip. And evidence shows that the actual flip itself takes less than 100 years. So if if it happened, it would happen, within like a young person's lifetime. They'd grow up with the poles being one direction, and then, by the time they were old, they'd point the other way. And
Wow.
in the meantime, it's interesting that it probably has like a big effect on like a lot of organisms and biology. But there you go. All right. So magnetic fields, I don't mean to make them sound weirder than they are, but it's really, I think Kylie said it better than I have. It's just comes down to, just remember that opposites attract. That's the idea. This shows it again, right? Imagine if you dangled a giant magnet, in outer space. Well, the north end would get pulled towards the south end of this, magnet that seems to exist inside of our planet. But let's challenge that weird idea that a giant bar magnet just happens to, be sitting inside of our planet, because we know that's not true. We were talking about how the planet has these layers, right, of the mantle and the inner core and the outer core. So obviously there's no space for a giant bar magnet. So where is it coming from? Well, the source of the magnetism inside of Earth is created by the motion of electric charges, just like any electromagnet. So there's really kind of two types of magnets. There's permanent magnets, where the magnetic field is locked in, and that's fine, and kind of it can happen in certain materials, but that's definitely not what is happening inside of Earth, because you can't have a permanent magnetic field locked in a planet with a molten interior, right? If the inside of our planet is so hot that it's a liquid, then there's no way that that type of substance could support a permanent magnetic field. You the only way you can have a permanent magnet is to have, certain elements, like the really strong magnets that you see today are neodymium, which is a particular, an element from the periodic table, and called considered one of the rare earth elements. And it's really good at locking magnetic fields. And so when they make a neodymium magnet, they heat it up, expose it to a strong field, like they have an apparatus with a really strong field made by a current, and then as that neodymium cools into its, it basically like a like I can think of the word, but anyway, it's you've got this like spot where the metal is cooling into its shape, and the mold. There you go. So you got the mold, and the magnet cools into its solid shape. Great, then it's done. But if you were to heat it up again, you'd ruin the magnetic field. You would ruin that permanent magnet. Every permanent magnet, if heated up or exposed to any high energy, will not be a magnet anymore. You can demagnetize it. So point being is that can't be where Earth's magnetic field is coming from. It's not a permanent locked in magnetic field. Instead, it's like that, it's a dynamic field, like the kind that's created by running a current through a wire. So this is how electromagnetic magnets work, where a strong current is run through a typical, usually copper wire, which is wrapped around some sort of core to help direct the field. And the motion of the current and the moving electrons that are associated with that current creates the magnetic field. Well, that's actually the principle that exists behind Earth's magnetic field. But that also begs the question, well, where's the giant wire inside of the planet, right? Do we have a coil of giant wire? Well, no, but we do have a bunch of right here. So we've got this heat that's driving convection of fluids that contain charged particles. So we have this molten rock, and that molten rock has lots of charged particles, and all those charged particles are being freed because of the molten nature of the rock, kind of in the same way that you can free electrons with friction, like rubbing your feet on the carpet and having your hair stand up on end. So that's what's happening on a global scale inside of the planet. And so all this freed up charge is then spinning as the planet spins. So as the planet rotates, the charge inside takes the rotational spins as well. And then that overall effect acts like a big coil or a series of side by side coils, essentially one big electromagnet. And if it wasn't for Earth's rotation, we wouldn't have we wouldn't have like this big, we wouldn't have such a strong field. So the kind of necessary ingredients of a magnetic field are going to be a molten interior that's heavy in metals. So you have to have the metals to kind of free up the electrons. Have enough electrons in the first place. It has to be molten, and in order to have the source of energy. So that's sort of the to create the static electricity. And then you have to have a global rotation rate, and of course ours being 24 hours thereabout. And so those are the conditions that will lead to a terrestrial planet creating a strong magnetic field. And when we look at the other terrestrial planets, they don't meet that criteria and they don't have strong magnetic fields. So looking at Mercury, Venus, and Mars, none of them have really almost any magnetic field at all. Mercury and Mars truly like zero magnetic field. And then Venus, a really weak one. And in all cases, it's because they're missing one of those key ingredients. Either, relatively fast rotation around the axis, or having a molten core. All right, this is we already talked about the regular reversing in polarity. I didn't sort of justify why the heck that happens. It's Just think of it as that these conditions that create the magnetic field are inherently unstable. I sometimes compare them to like holding a pencil on top of your finger, and you can kind of balance that pencil there and kind of move your finger around to keep it balanced. But as soon as you make one wrong adjustment, it's just going to flip over, and that's called a unstable equilibrium. So it is balanced, it's in equilibrium, but it's not. It's any like significant push is going to cause it to flip out of that unstable equilibrium. And so that's exactly the principles behind, these the creation of poles like this. They're always in an unstable equilibrium with just one big perturbation, one big, misadjustment, so to speak, away from flipping. And there might be some external influence, something that happens throughout the solar system that causes the regular flip, or just a combination of variations with our orbit over time. But there's, for whatever reason, we have this sort of this regular flipping. And then there's just like the pencil that you're trying to balance on top of your finger and keep upright, there's always a constant kind of like moving it around to keep it balanced. And we can see that over the period of just decades and individual years by tracking the location of the pole, which is shown in the figure on the right, where you can see the location of the current magnetic south pole, right, up in the north of the planet. Where it was when it first started to be observed back in the 1600s, and then 1700s up to more modern, detailed, and frequent measurements starting in 1904, and then seeing it track way up to actually be pretty close to the exact geographic North Pole. And the geographic poles are just based on the rotation. So that's right where our rotational axis runs. And so, now our magnetic pole is, pretty close, right? But sometimes it can be, a few hundred miles away. Then there's that influence into space, which I mentioned. So the magnetic field created inside of the planet, talked about what the poles mean. Then the effects of the field spread out into space. And the scale that they spread is actually pretty accurately shown. So if you consider the diameter of the Earth, the effects of our magnetic field extend out around 5 Earth diameters into space. There would not be really much measurable magnetic field from Earth by the time you get to the moon, which is 60 Earth radii or 30 Earth diameters away. But lower down, there absolutely are. And what's important is that this entirely, includes our atmosphere. Our atmosphere is only 100 kilometers thick, up to about 150 kilometers. So it'd be too small to even show up in this diagram. So that's crucial because you can think of the atmosphere as being entirely encased by Earth's magnetic field. The field lines, just like any magnet, right, are concentrated at the poles, right? So we've got the poles of the planet. So the south pole of the planet, north pole of the planet, which of course would be, unfortunately not included in the figure, but it would be, the south magnetic pole and north magnetic pole respectively. But what is shown are some kind of aspects of the magnetic field, these things called the Van Allen belts, which are where lots of charged particles end up getting concentrated. So in other words, a bunch of free electrons. But wait, are these the free electrons I was talking about that are, the ones that make the field in the first place? Well, no, because those are locked down in the mantle, right below the crust. No, these are other charged particles. They get created in all kinds of ways that are actually streaming from the sun. So this is the first time we're mentioning a very important thing that the sun does, besides just making light, which we have talked about. The sun produces something called the solar wind. And it emanates from the sun. It they basically is directed away from the sun in all directions, just like the light that's created from the sun. But unlike the light that moves away from the sun, the solar wind is not light. The solar wind is a stream, a constant flow of charged particles, primarily electrons, but also some alpha particles, some of other small ionized nuclei, and some individual protons, but mostly electrons. By far, they're the lightest, the easiest thing to be created, and it's the sun. It's because the sun is doing all this high energy physics in order to glow in the first place, and a byproduct of that is just a bunch of ejected electrons. Have you ever heard the sun described as a plasma? That has a lot to do with it because a plasma is an ionized gas. Ionized means you've lost all of your electrons, or every individual molecule or atom has. Where do those electrons go? Well, they just kind of got freed up. Well, a bunch of them get pushed away from the sun. There's just this really the steady flow of electrons just streaming out into space. And we call it the solar wind. Not an actual wind, because of course a wind would require a fluid, and there's no fluid in space. It's just the name given to this stream of electrons. Here's the thing about it. It on its own, it would just wipe away our atmosphere because all the heat that is delivered from every individual electron would cause our atmosphere to heat up and essentially cause it to boil away. Not right away, but over time, we would just get a thinner and thinner atmosphere as all the nitrogen, oxygen, CO2 molecules in that atmosphere would get excited to high enough speeds that they would just gradually escape into space. So that means that if we did not have a magnetic field, we would not have an atmosphere. And that is just a pretty much, you know, clear statement for the type of atmosphere that we have. Venus is able to hold on to a much different atmosphere with almost no magnetic field, but of course their atmosphere is totally inimical to life. It's, creates these incredibly high temperatures. So because it's so dense, over 100 times denser than ours. But Mars is a good example of a planet that doesn't have an atmosphere and doesn't have a magnetic field. Well, those two ideas do go hand in hand. So there's a really strong correlation between being able to have an atmosphere and having a magnetic field to keep that atmosphere. All right. So you can thank the magnetic field for being able to breathe. So what about where the field lines kind of come down to the surface? Because if the magnetic field is necessary for keeping the atmosphere, then, and we'll talk kind of about how it's able to protect us from the solar wind, the vulnerable points are where the field lines are, instead of being kind of stacked up and almost creating a barrier against the solar wind, instead where they kind of coalesce and point right down to the surface. That means that we have these regions where maybe the magnetic field is not as efficient at stopping the solar wind. Okay. Well, that's why we have the auroras, both the aurora borealis in the north, right, high latitudes, the geographic north, the magnetic south, and the aurora australis in the negative latitudes, the southern latitudes, the magnetic north. Okay. Particles are funneled along the magnetic field lines until they reach the atmosphere and excite molecules in the air. That's what creates the glow known as the northern lights. Okay. So to talk about that, we'll also go back to the kind of open question that I proposed about how the magnetic field kind of stops the solar wind in the first place. Well, it comes down to the idea I mentioned briefly before that magnetic fields interact with charges. They exert forces on charges. So if the electrons, which you can think of as every one of these green dots that compose the solar wind, come in, they're streaming through space, no problem, but then they interact, they all suddenly experience Earth's magnetic field, and that field starts to exert a force on them. And it will exert a force that causes them to spiral along the field lines. So they will actually spiral along the field lines. The exact motion isn't shown. You just kind of see them following the field lines, which is a fine way of thinking about it. So they are funneled or follow the field lines. If you were to see their exact motion, it's actually a helical spiral. And then by following those field lines, they cannot make their way to, say, the equatorial latitudes. There's no way because they can't jump across field lines. So none of the electrons are able to make it to anywhere near the equator or the smaller latitudes. But they are able to get funneled down to the northern latitudes. And in doing so, they hit the atmosphere, they release their energy, they cause, some ionization of gases, right? They do excite molecules, give them greater speeds, right? And that shows up partially as an emission of light. It also causes, the atmosphere to, like I said, become more energetic and, just like a boiling liquid, take up more space. So the atmosphere kind of swells up. When there's a big solar storm, that actually causes significant swelling of the atmosphere, so much so that it can affect certain satellites. But Is it enough to sort of boil away our atmosphere? No, because it's such a small proportion, right? So even though we have, some of the solar wind making it to the poles, it's just some, and it's just a small portion of the atmosphere that's being affected, and a sustainable amount. You know, case in point, the atmosphere has, been doing well for a long time, but it is susceptible to to changes, but there's no evidence that we're in danger of the solar wind, unless the unless it was too significantly changed, right? What if the solar wind doubled in strength or something? Well, that'd be something to consider. But that aside, there's no, just light and a little bit of swelling being created by the incoming energy. Here it is seen from the surface, seen from space, right? So the glowing atmosphere as the solar wind collides with it. All right, so 9 minutes. Let's see what I can get done. So let me see. Yeah. So I mentioned the atmosphere a lot. So let's run through some numbers here. So if we think about the building blocks of the solar system, as well as all of the universe, it's hydrogen and helium. So remember how we talked about the solar system being formed in the first place with that, that early nebula and becoming the disk. Well, this it would have started with kind of this proportion. And and then we're asked, do hydrogen and helium have large or small masses compared to other elements? And they have really light ones. They're really low on the periodic table. So just I'll let you know that they're in fact the lightest elements. Their atomic masses are 2 for hydrogen, and at least for hydrogen 2, and 4 for helium. Although a lot of hydrogen doesn't actually have a mass of 2, it just has a mass of 1, because typical hydrogen is just a single proton. But this is referring to deuterium, which has a proton and a neutron, which is interesting. I'm not sure why they went for deuterium, because it's much more rare. Oh, I see, because they're talking about the molecule. Okay, so hydrogen 2 is the molecule that's formed by hydrogen. And so in our atmosphere, all the hydrogen is in the state of hydrogen 2, which is 2 separate hydrogen atoms, each the standard version of hydrogen, which is just a single proton, rather than the isotope I was talking about, known as deuterium, which is hydrogen and a neutron, which is quite rare. It's actually what creates heavy water. But if you just have standard hydrogen, 2 of them come together, they form a really stable molecule. And this happens with a lot of gases, or elements that become gases at sort of Earth temperatures. You have lots of these called diatomic molecules as the most stable molecule that can exist, for that particular element. So hydrogen doesn't tend to be in an atomic state, with just a single one. Instead, it's 2 together. They bond together because of the bonds between their electrons, called molecular bonds. So that's each of these is 2 hydrogen atoms forming a little pair, and a really small molecule, but technically a molecule. All right. So might kind of call them an atom, but technically they're a small molecule. So very light atoms move very quickly and easily escape gravity's pull. Okay, so this ties into what I was talking about the atmosphere being able to escape if you heat it up too much. And that's actually why we don't have just hydrogen in our atmosphere. And we don't even have helium in our atmosphere. Our atmosphere in no way could hold on to those light elements. It, no chance, even with the protective magnetic field, you know? So instead, our atmosphere is composed of heavier gases, heavier elements. Not the heaviest, but heavier. So we don't have any hydrogen or helium in our atmosphere. Whatever is created escapes into space over time. All right. It's able to achieve escape velocity. And it basically comes down to this direct calculation between what's the typical thermal velocity of the molecule, to a probabilistic argument, and then how fast does it need to be going in order to escape gravity, like a rocket, and it has an escape velocity. Well, it turns out that when you run those numbers, a lot of the molecules are able to be going fast enough, so over time they all escape. So instead, our atmosphere, okay, and this is this one actually is an early atmosphere. So back in ancient history, well before there was life that breathed oxygen, the atmosphere would have been 58% H2O or water, a large amount of carbon dioxide, which is easily forms. So it's a key building block of a lot of atmospheres. Venus and Mars both have carbon dioxide in their atmospheres. Even though Mars' atmosphere is almost non-existent, it is there, and it's mostly CO2. Sulfur dioxide, nitrogen, and noble gases like neon, xenon, and so on. All right. But that atmosphere changed over time. One big change was life itself. So the evolution of life is the reason that we have this 21% oxygen. As far as we know, there is no chemical process other than life that can create oxygen atmospheres. Period. And people, scientists have really looked into any sort of just like purely mineral based, like a special type of volcano or some interaction between, different types of, bubbling oceans that, but maybe not even an ocean of water, like all, but never is free oxygen created. Only the chemistry that's involved with the type of life that we know of, right? The type that's on Earth and the only type that we know of is, only through those chemical chains of interactions is free oxygen a byproduct. So when we look at, space and we look for a planet that has free oxygen, we're doing that in hopes of saying, okay, well, if it's got an oxygen-rich atmosphere, got to have life, right? And we could be wrong, but it'd be a great starting point. We haven't confirmed any planet outside of our solar system that does, but that's largely because of kind of limited ability to do so. It could be achieved in the future, in other words. But also, the nitrogen level now is predominant. Our atmosphere is predominantly nitrogen. Interestingly, because we don't breathe it, and neither do plants, right? Plants absorb the carbon dioxide, of which there's a tiny amount, right? They produce oxygen as the byproduct, of which all this oxygen dependent life has evolved to take advantage of, and then the nitrogen is just kind of around as a passive medium, right? So, but no organisms at least rely on the nitrogen in our atmosphere. Okay. And it is noteworthy how small the carbon dioxide amount is because it's sort of in a state where it's all locked up at any given point, right? The carbon dioxide is all, in all the plant life or, locked up in minerals, and only a little bit of it is ever free in the atmosphere at any given point. And that's sort of this interesting stability point that our atmosphere has reached, along with the ecosystem that exists alongside the atmosphere, right? Or, as a result of it. All right, so I have to kind of wrap things up. Let me see what I want to say next time. Just click hold on. There we go. Got 1 minute. All right, so yeah, because this isn't, yeah, there's the cycle a little bit, and then it just gets into the greenhouse effect. And it's got all these slides talking about the balance. So I'll post the video because I will cover this with the other class. But for this class, you need to look over these slides yourself. You can look at any of the videos that talk about it. But other than lecturing in the other class and me posting that, we won't spend more class time on it. And just to point out what it is that we will not be spending more class time on, it's the CO2 cycle and how that can be related to climate change. Okay, understanding what drives climate change, and kind of like what has been happening with the human effects, and why how we've had caused some really dramatic effects by changing the pattern. Okay, all right.
Do we have a quiz in class tomorrow?
No. So the quiz on chapter 8 is the one that I just posted on Canvas. And so we definitely will not have a quiz tomorrow because the only one would be 8, but instead it's on Canvas.
Oh, okay. I just
Yep.
didn't know if we were doing the chapter 9 lecture tomorrow and a quiz after.
No, no, we won't do that. I'll never try to do them back to back like that, although sometimes I'll be finishing a lecture, but I would never start it and do the quiz in the same day. But I could see asking though. Yeah.